Okay, so welcome to the last in this seminar sequence for this term. We'll carry on in the new year. So as usual, we have people muted, but please do ask questions in the chat, and Christina and I will curate and either pass them on to the speaker immediately or wait until the end, whatever seems more appropriate. Also, co-authors are encouraged to answer questions in the chat if they feel like it. I see we have at least two here. But without further ado, it's a great pleasure to have as our last speaker of this calendar year, Gwenaël Joret, who's going to talk on sparse universal graphs for planarity. Thanks.
So thank you very much, Alex, for this lovely introduction. So this is a joint work with Vida Dujmović and Louis Esperet, who are attending. Hi, Vida. Hi, Louis. And with Cyril Gavoille, Piotr Micek, and Pat Morin. And it's about universal graphs for planar graphs. And so let me dive directly into the topic. So what is a universal graph? So typically you look at some set of graphs and you want a graph that contains every graph in your set as a subgraph. So what you typically do is you pick some class of graphs of interest, say, for instance, trees, graphs of maximum degree at most 10, planar graphs, whatever class of graphs you like. And what you typically do is you fix the number of vertices. Say you look at graphs on n vertices, and you want a universal graph for the n-vertex graphs in your class, and you want a nice one. So that's typically the setup in this area. And what is a nice universal graph? It's a graph that has few edges. Obviously, you could just take a complete graph on n vertices. That's definitely universal, but I think you would agree it's not truly interesting. And so the way we measure the quality of a universal graph is by counting the number of edges, and we would like to have as few edges as possible. So that will be the main topic of this talk. Towards the end of the talk, I will talk a little bit about a related notion, which is induced universal graphs. And in that case, we want to contain the graphs we care about as induced subgraphs. So there it's a bit different, but this I will keep for the end of the talk. So for most of the talk, we can just focus on universal graphs, and we care about realizing the graphs we care about as subgraphs. So during the whole talk, the question that will motivate this talk, and the thing I would really like to talk about here is, what is the minimum number of edges in a universal graph for n-vertex planar graphs? I should mention that there are some practical applications to this, in particular in VLSI design. I don't really know about them, but personally, I think it's a really nice question on its own. And I would like to share my enthusiasm for these questions in this talk. But what I will do first, I won't start with planar graphs right away. I will try to give you a gentle introduction to the area of universal graphs and try to give you an idea of what are the different tools we can use to build universal graphs, not only for planar graphs, but for other classes of graphs of interest. So what are the basic tricks we can do in this area? So definitely, without any doubt, the main tool in this area is separators. So for the purpose of this talk, a separator of a graph, of an n-vertex graph, is a subset of vertices, so that when you remove it, you can arrange the connected components of what's left in two sets, say left and right, each of size at most 2/3 n. So if you can do that, your set of vertices that you removed is called a separator. And of course, we would like to have small separators. If you have small separators, this will be really useful to build universal graphs. So in order to build some intuition and also as a warm-up for the rest of the talk, I suggest we start by looking at trees. So n-vertex trees. How can we build a nice universal graph for n-vertex trees? This is not really difficult, but lots of the basic ideas that we are going to see here, we are going to meet them again in the rest of the talk. So it makes sense to spend some time on trees. So as you probably all know, a nice fact about trees is that there is always a vertex of your tree, which is itself a separator of the tree. So let me quickly recall one way of proving the fact that you have such a separator in your tree. So one way to see this is first orienting the edges of your tree always towards the bigger side. So every edge of your tree is oriented. And because you have a finite tree, well, there is a sink. And so meaning all the edges are oriented towards that vertex. And that sink will be your separator. So why is that? Well, look at that sink. Let's call it V. Then when you remove it, every component will have size at most n/2. And now it's only a matter of arranging them into two sets of size at most 2/3 n. One way to do this is to order the components in non-increasing order of sizes. And then for the left side, you take the first component and then you take as many components in order, but respecting the upper bound of 2/3 n. So you will definitely take at least one component since the first one is of size at most n/2. And now, well, why is this good? Well, obviously by definition, you have at most 2/3 n on the left, but we also need to check that we took at least 1/3 n in, so that on the right, we have at most 2/3 n. So why is that the case? Well, let's look at the first component we didn't take. If it's of size at least 1/3 n, then it means the first component was of size at least 1/3 n, and so we are good. We took at least 1/3 n. If it's of size less than 1/3 n, then why didn't we put it on the left? It's because we already have 1/3 n on the left. So in both cases, we have at least 1/3 n on the left. So bottom line, in a tree, there is always a vertex, which is a separator for our definition of separators. And if I told you, please go ahead and build universal graphs, a nice universal graphs for trees, this might be your first reaction. Let's try to use a separator, make it universal and recurse on each side and build a universal graph in this way for trees. All right, so pick a vertex and make it adjacent to everything else and then recurse on each side. Now, each side will have at most 2/3 n vertices, but of course, one side will have at most half of the vertices. So you can imagine that left will have at most 2/3 n and right will have at most n/2. So you could try something like that. So that would be a first attempt. Create a vertex, make it universal, adjacent to everything. And then on one side, you put your construction for 2/3 n vertices. And on the other side, you put your construction for 1/2 n vertices. And hopefully it should be clear that this is universal for trees. And if you do the calculation, which I'm not going to do here, you get a number of edges, which is about n⁻⁴ if you do that. So this is already better than just taking a complete graph, which has quadratically many edges, right? So this is a definitive improvement on complete graph, but this is not the best you can do. So intuitively, what is going wrong here? What is going wrong is that we are not splitting the space of vertices in half exactly, right? So we could have a bit more than half. We have 2/3 n possibly, and this creates more vertices and this accumulates, and this is why we have extra edges as well. So intuitively, it would be better if we could split, if we have something where we could really split the graph in half. And that's what we typically do when we build universal graphs. So instead of using separators, one option would be to use perfectly balanced separators. So that's a stronger version of separators. So perfectly balanced separator would be a separator so that when you remove your vertices from the graph, there is a way to arrange the components in two sets of exactly equal size. So they will have exactly the same size. So in particular, they will have size at most n/2, but I even ask more strongly that they have the same size. So that's a strong notion of a separator. That's the best you could hope for in terms of separating your graph. And it would be too much to ask that a tree has a vertex which is a perfectly balanced separator. This is not true. But if you are fine with removing log n vertices, then you can find a perfectly balanced separator of that size in a tree. And I will quickly recap how to find such a set, because we are going to generalize this. We are going to use this for other classes of graphs than for trees. So it's good to see how we can, one way of doing it at least. Okay, so how do we get perfectly balanced separators for trees? Well, one way is to use the standard version of separators, so just one vertex, which is a 2/3 n separator, and recursively take a separator on each side. So I take the first separator, I call that vertex 1, then I recurse on each side, and I take a separator again and again, again. And this way I have the following recursion tree, right? So this is the first one I took, then I took these two vertices, one on each side, etc., etc. So these gray edges, they are just there to model the recursion tree. They are not edges of the graph necessarily. But the one thing to observe is that the edges in your graph, so in this case it's a tree, but the edges in your graph, they must connect a vertex to an ancestor of the tree, right? Because like the first vertex you took, well, possibly it's linked to everyone. But now when you took these vertices number 2, well, the one on the left can only be linked to vertices on the left, and the one on the right can only be linked to vertices on the right, etc., etc. So the edges of your graph, they are part of the transitive closure of this tree, right? So they can only link a vertex to an ancestor. And using this observation, then we can find perfectly balanced separators in the following way. What we can do is we can look at the leaf of your recursion tree, and then we can take in the recursion tree the path up to the root. So this is about log n vertices, say log in base 3/2 of n at most. And when you do that, well, there is an obvious notion of left and right. And there is no edge between vertices on the left and vertices on the right, simply because you don't have any ancestor relation between vertices on the left and vertices on the right. A vertex on the left cannot be an ancestor vertex on the right, and vice versa. So this separates, these log n vertices separates left from right. And you can do that starting from any leaf of your recursion tree. So you could scan all the vertices of your graph starting from the leftmost leaf in your recursion tree in the following way. So you take the leftmost leaf, you look at the corresponding orange set, this vertical path, then the left side is empty, the right side has everything. And then when you go from one leaf to the next one, the new vertices that join the left side will be a subset of the previous orange path. So there will be at most log n vertices that join the left side. And so when you do this scanning, you will find a point where you split roughly in half up to log n vertices. And when you find that point, then you make it exactly equal by removing up to log n vertices from the BO side. Right, so that's one way of finding perfectly balanced separators. And once you have this, well, there is an obvious construction to do. Take your perfectly balanced separator, say it's of size C log n, make it a clique, and make it universal to everything. And then you recurse on two sides of exactly the same size, where you divide the remaining number of vertices in half. So how many vertices are left? N minus size of this clique, so n minus C log n. And then you put over 2 on each side, and then you put recursively the construction on each side. So hopefully it's clear that this is universal for trees, for n-vertex trees. So what is nice is that it's really economical in terms of vertices. So this construction has exactly n vertices, right? So we spend C log n, and then we have n minus C log n, which is divided in 2 on each side. And how many edges do we have? Well, in one step of the construction, we have roughly log n times n edges, right? So you also have the edges of the clique, but they don't cost much. So roughly in one step of the recursion, you have n log n edges, and you have up to log n steps. So this is an n log squared n upper bound on the number of edges. Right, so this is an easy construction of a universal graph for trees, for n-vertex trees with n log squared n edges, and this is almost optimal. You can do a little bit better. So Chung and Graham proved that you can do n log n, and that's best possible. So there is a way to shave off one log n factor, but the construction is more complicated. It's also based on separators, but it's more involved. And I won't need this for the rest of the talk. On the other hand, this construction I will use in some form later on. Okay, so that's so that was for trees, but as should be clear, we didn't really use much about trees in this construction. We only use the fact that they have small separators and small perfectly balanced separators. So this works more generally when you have small separators. Sorry, but before that, I forgot to tell you about the lower bound for trees. So I mentioned that n log n is best possible for trees. There is a simple reason for that. So your tree could be a star. So then you have the vertex of degree n minus 1. Or it could contain 2 stars each on n over 2 vertices. And then you have 2 vertices of degree roughly n over 2. Or it could contain 3 stars each of degree on n over 3 vertices, and then you have 3 vertices of degree roughly n over 3. So this means that when you look at your universal graph and you sort the degree sequence in non-increasing order, then that degree sequence must dominate, well, roughly n over 2, n over 3, n over 4, etc. So this gives you an n log n lower bound on the number of edges for trees. Okay, so n log n is tight for trees. Okay, so let me go back to separators. And so as I mentioned, what we did for trees is not really specific for trees. So you could look at any class of graphs which say is closed on the subgraphs for good measure. Probably induced subgraphs is enough. And imagine that you are guaranteed that in your class, the n-vertex graphs have small separators. Say they have separators of size at most s of n. So it could depend on n. You probably know, for instance, that planar graphs have square root n separators. So you can think of that, for instance. And so the proof we did for trees, where we rip off one vertex, which is a separator at each step, and we look at the recursion tree. Well, you can do that with any form of separators, and then you get perfectly balanced separators of size s of n times log n. So you pay an extra log n factor. And then you could use that to build a universal graph for n-vertex graphs in your class in exactly the way we discussed, right? So you put a clique on a number of vertices which corresponds to the size of the balanced separators, the perfectly balanced separators you're guaranteed. You make it universal, you recurse on each side, you split exactly in half the remaining number of vertices. And then we get this type of bound on the number of edges. So the size of the separator times n times log squared n, right? So in the case of trees, this s of n is just 1. So this is the case. So why do you get perfectly balanced separators of size s of n times log n? Because the proof we did here works. The only difference is that instead of having one vertex at each node of the recursion tree, while you will have a bunch of vertices which correspond to the separator you ripped off at that step. But otherwise, there is no difference essentially in that proof. Okay, so when you have small separators, you have sparse universal graph in this sense. And for good measure, since I already mentioned the case of planar graphs where you have root n separators, I should mention that if you have separators which are a bit bigger but still strongly sublinear, like n to the alpha, where alpha is strictly between 0 and 1. So think of root n, for instance. Well, in that case, the log factors that disappear. They are amortized because you have a geometric series. So when you do the argument for perfectly balanced separators, you get one of size big O of Sn. You don't pay the extra log n factor. And same when you do the universal graph, again, the second log n factor disappears in the geometric series. So in that case, if you're looking in this regime, then you really get a universal graph where the number of edges is s of n times n. So size of the separator times n. Okay, so that's hopefully shows that having separators, and in particular having perfectly balanced separators, is really a really useful tool for building sparse universal graphs. And now whenever you have a class of graphs that enjoy small separators, then you have a sparse universal graphs. So that was the first idea I wanted to convey. So let me talk a little bit about planar graphs, since that's the topic of this talk. So I already mentioned that planar graphs have square root n separators. That's a famous theorem of Lipton and Tarjan. And so this implies that you have square root n perfectly balanced separators, and you get universal graphs with n to the 3/2 edges for n-vertex planar graphs. So square root n times n. And that's essentially what Babai, Erdos, Chung, Graham, and Spencer did in 1982. And that was the best known bound for planar graphs. So what I will try to do in this talk is to tell you how to improve on this n to the 3/2 bound for planar graphs. Obviously, we are going to need to use something more than just separators. But before I do that, let me talk a little bit about some other classes of graphs which are somehow related to planar graphs and that are generalizations of planar graphs and that enjoy small separators, just to give you some examples of nice classes of graphs with small separators and hence having universal graphs with, that are quite sparse. So one way to generalize planar graphs is to look at the so-called kissing coin representation of planar graphs. And then you can look more generally at intersection graphs of touching boards in RD, right? So the vertices corresponds to boards. Every two boards are either disjoint or they touch. And a very nice theorem of Miller, Tang, Thurston, and Vervasis is that these graphs have strongly sublinear separators. They have separators of size n to the 1 minus 1 over d. So that's really nice. So when these two, you get back the square root n separators for planar graphs. And then you can use that to build universal graphs for those graphs, for these n-vertex graphs in that class. So you get the size of the separator times n, so you get a bound of n to the 2 minus 1 over d on the number of edges for your universal graph. So that's one way of generalizing planarity. A second way, which is very different, is to look at graphs drawn on a fixed surface. And then if you fix the surface, you have square root n separators. So you get an n to the 3/2 bound on the number of edges in your universal graph using these separators. And more generally, if you forbid any graph H as a minor, you have square root n separators again. So you get, again, the same type of upper bound on the number of edges for graphs forbidding a fixed minor. So that's a second way of generalizing planarity through minors, through excluding a minor. And a third way of generalizing planarity is to look at drawings of your graph in the plane where you allow crossings. You allow at most k crossings per edge. So if you do that, you have the notion of k planar graphs. And they also, for fixed k, they also enjoy square root n separators. So that was known for a long time, but the tight dependence on k was sorted out by Vida Dujmović, David Epstein, and David Wood in 2016. So it's square root k times square root n. And so you get, again, same type of bounds on the number of edges in your universal graph. Right, so these are some examples of classes of graphs of interest around planar graphs that also have these sparse universal graphs. Okay, so now let me go back to planar graphs. And so the main result done together with Louis Esperet and Pat Morin is that we can build universal graphs that have a near linear number of edges for n-vertex planar graphs. So I should emphasize that this work relies heavily, it builds heavily on a previous paper with a superset of authors, including Vida Dujmović, Cyril Gavoille, Piotr Micek, and Pat Morin. And that was about induced universal graphs for planar graphs. I will say a little bit at the end of the talk, some words about this at the end of the talk, but some of the machinery we developed there, we reuse in this paper. Okay, so we need some new tool to get better universal graphs for planar graphs. And I'm going to explain what new tool we are going to use. And to introduce this new tool, I first need to talk a little bit about tree width. I'm not going to define what tree width is. I'm just going to say that it's a measure of how similar your graph is to a tree. Trees have tree width 1, and graphs with bounded tree width, they somehow look like trees or behave like trees. So what will be important for this talk, and this is the only fact we need to know about tree width, is that if you have tree width k, you have a small separator. You have a separator of size at most k plus 1. So for the purpose of this talk, you can think of graphs of bounded tree width as graphs with constant size separators. So small tree width implies small separators. And in a sense, up to constant factors, having small tree width and having small separators is the same thing. So Dvorak and Morin proved that if you have a graph that has a separator of size at most k, and all your subgraphs have also separators of size at most k, then your graph has tree width at most 15k. So up to a constant factor, if you don't really care about the details of the definition of tree width, then tree width is the same thing as having tree width at most k is essentially the same thing as having small separators. And that's the idea we are going to use in this talk. So whenever I say small tree width, you can think of having small separators. I'm going to use that as a synonym. Okay, so I was saying we need a new tool for working with planar graphs, and this was provided in part by Michał Pilipczuk and Sebastian Siebert 2 years ago, and they proved this fantastic theorem about planar graphs. This is one of my favorite theorems, and it says the following: take your favorite planar graph, then there is a way to partition the vertices of your planar graph into geodesics, so shortest paths in your graph. In such a way, so like look at these orange paths, for instance, on this planar graph here on the left. In such a way that when you contract each of these geodesics into a vertex, so you're defining some minor, then that graph has small tree width at most 8. So let me repeat this a bit differently. Given any planar graph, there is a way to select shortest paths, disjoint shortest paths in your graph, contract them into a single vertex each, in such a way that after that, you of course still have a planar graph because it's a minor, but more importantly, you have constant size separators after that. You have bounded tree width, so you have constant size separators. And that's really nice. And the proof is not too complicated, but it's really clever. It's really nice. It's one of my favorite results in recent years. And so that's not exactly the tool we are going to use. We are going to use a variant of this theorem. And to explain the variant, I need to introduce the notion of a strong product of two graphs. So strong product is the easiest type of product to define because you put all the edges that would make sense. So when you look at the strong product of two graphs, well, you have in your product, you have a vertex for each pair of vertices, one from the first graph and one of the second graph. So typically we think of the first graph as being the horizontal graph and the second graph as being the vertical graph. And then how do you define the edges in the product? Well, look at two vertices in the product. So for instance, these two here, hopefully you can see my mouse. Thanks. So you put an edge if they project in each dimension, if they project either to a vertex or to an edge in the graph. So here, vertically, they project to an edge, and horizontally, they project to an edge. So you put this diagonal red edge. Now, if you look at these two vertices here, you put an edge because vertically, they project to a vertex, and horizontally, they project to an edge. Right? So as pictured here, if you take the strong product of two paths, you get this grid plus crosses in the cells. So why are strong products relevant to this discussion? It's because with these co-authors, so with Dujmović, Micek, Morin, Ukert, and Wood, last year we revisited the theorem of Pilipczuk and Siebert, And by tweaking a little bit the proof, we got the following statement, that every planar graph can be realized as a subgraph of the strong product of two very simple graphs, a graph of bounded tree width at most 8, and a path. So this graph here on the left, which is in this case a tree, is supposed to picture a graph of bounded tree width, and this is a path. You look at the strong product, and there is a way to choose your bounded tree width graph and the path, so that in the strong product, you contain as a subgraph the planar graph you care about. So for every planar graph, there is a way to do this. And so this turned out to be quite useful for a variety of problems, because it shows that planar graphs, which are not that simple in terms of structure, well, in fact, there is a kind of, they can be realized as subgraphs of something which has a very rigid structure, these products of something that looks like a tree and a path. Okay, and that's the tool we are going to use to get better universal graphs. So as you might have guessed, now our main theorem is not really about planar graphs, but it's about the strong products of a bounded tree width graph and a path. And we want to realize all the n-vertex graphs that can be realized as subgraph of a bounded tree width graph and a path. And we are not fixing the bounded tree width graph, right? So once again, I'm looking at all the n-vertex graphs that can be realized as subgraph of some h times p, where h is some graph of bounded tree width t, of some graph of tree width t, say, so bounded tree width, and some path p. And for those, if you bound the tree width, then we get a near linear upper bound on the number of edges in the universal graph we built. Dependence on tree width is t squared. So in the case of planar graphs, this is a constant. Okay, so what I'm going to do is I'm going to try and explain what are the main ideas in how we construct these universal graphs for products of a bounded tree width graph, for subgraphs of bounded tree width graph times a path. I'm not going to be able to describe the full construction fully, so I'm just focusing on the main ideas. So first, we are going to clean up the problem a lot. Well, a little at least. We are going to clean up the problem. So we are looking at n-vertex subgraphs of a bounded tree width graph. So we have some bound t on the tree width, and times a path. And obviously, so say this is h, the horizontal graph, and p is your path. Then obviously it doesn't make sense to look at a path with more than n vertices, since you're looking at n-vertex subgraphs anyway. So you can assume that p has n vertices. And for same reason, there is not really any sense in looking at h that has more than n vertices. So you could think of h as having n vertices. So now you're looking at some product with n squared vertices, but you're looking at n vertex subgraph of those. But there is a subtlety here, is that we are not fixing h. We are not taking one specific h, one specific graph of, say, tree width 8 times a path and looking at the n-vertex subgraphs of those. Actually, we let h be any, we let h vary. We let it be any n-vertex graph with tree width t, and we want to handle all of those collectively. Right, so that's a small subtlety. So how could we take care of collectively all the n-vertex graph with tree width t? Well, that's exactly what universal graphs are good for, right? We know how to build universal graphs for bounded tree width, because this is the same as small separators, bounded size separators. So we have seen a construction of how to do that. And that's a single graph. Such a universal graph is a single graph that will contain all the n-vertex graph with tree width t as a subgraph. So the first step, of course, is to get rid of h, which is a variable, and replace it by d, or one choice of a universal graph for n-vertex graph with tree width t. So that's step number one. We clean up the picture in this way. So now we are thinking of, instead of h times p, we think of universal graph for tree width T times P. Okay, so now I will be a little bit more precise about this universal graph. So let me recall a few things. So tree width T implies separators of size at most T plus 1, as I already mentioned. This implies perfectly balanced separators of size T log n, roughly. And using the construction that we discussed at the beginning of this talk, then you would get a universal graph with about T and log squared n edges. So I keep mentioning T, but we should think of T as being fixed, as being an arbitrary fixed constant. But okay, so we could use the universal graph from the beginning of this talk, which is quite efficient. I'm not going to do that because I'm going to use another universal graph, which is slightly less efficient, which has slightly more edges, but which can be described very concisely, and this will be convenient for what follows. Okay, so this universal graph, which is not exactly the same as the one I described before, is the strong product of a clique on omega vertices. So that's omega is about T log n, and a graph which I called C sub log n. So let's look at C sub log n. C sub d will be the complete binary tree of height d plus all the edges in the transitive closure, right? So this is C sub 3, you have height 3, and then you have all the edges in the transitive closure. When you look at C log n, well, you go up to height log n, so you have n vertices. All the logs are in base 2, by the way, I forgot to mention it. So you look at this C log n graph, and of course, this C log n graph is modeling the recursion tree when we rip off these perfectly balanced separators at each step. Right? So that's what it's modeling. And what's happening when we take the strong product with this clique? Well, this is just a fancy way of saying replace each vertex by a clique of size omega, and omega is about T log n. Right, so I take this graph, and now if you picture it, you take this graph and you replace each vertex with this clique of size T log n, hopefully using the fact that the tree with T graphs have balanced separators of size T log n, it should be clear that this is universal for graphs of tree with T. So this is one choice of a universal graph for tree with T. As I mentioned, it's not as efficient as the one we discussed. Well, why is that? Well, if you just look at C log n, that graph has about n log n edges. And now when we substitute a clique of size omega for each vertex, then every edge is replaced with a complete bipartite graph with omega squared edges, right? So every edge gives rise to about T squared log squared n edges, right? So we have a blow up which is slightly more than what we have here in terms of the number of edges. But if you fix T, it's still n times polylog, and that's good enough for what we are going to do. And what is really nice is that it's a really easy way to think about this, this universal graph. Okay, so that's the one I'm going to use next. C log n times a clique. Okay, now let's simplify the primer a little bit more before going to the technical part. So what did we do so far? Well, first we were looking at H times P, where H was a bounded weight graph, but not fixed, and P a path. The path can have n vertices. This is what I mean by Pn. But then for the bounded weight part, we decided to replace this by a universal graph for tree T so that we can fix the left part. And I chose this C log n times K omega as a universal graph. That's one choice. We could have chosen another one, but that's the choice I'm going to make here. Right, so now I'm looking at this product here. So a universal graph for tree T here times a path. This contains all the graphs I'm interested in. And now I would like a universal graph, a sparse universal graph for n-vertex subgraphs of this thing. If I can do this, then I can go back to H times P, and then I can go back to planar graphs. So this is my new goal. And our main technical theorem is almost doing that. So what it's looking at, it's instead of looking at C log n times click times the path, it's dropping the click. So let's get rid of the click and let's look at C log n times the path. So again, let me show again C log n. So you have this complete binary tree plus edges in the closure. And then we take strong product with the path. So this is a quite easy graph to think about, right? You have a path of n vertices. So you have n rows, and each row looks like a copy of C log n. And then you have the edges in between rows as discussed. And so our main technical result is that for those graphs, we can find a universal graph with a near linear number of edges for n-vertex subgraphs of this specific graph. So this specific graph has n squared vertices. We look at n-vertex subgraphs of it, and we have a universal graph with few edges. That's really the main technical theorem in our paper. So you might say, well, how good is that? Because we were interested in n-vertex subgraphs of this thing, not of this thing. So the click is missing. But once you have a universal graph for this thing, you can simply take the universal graph and substitute in your universal graph each vertex by a click of size omega, and then it becomes universal for this thing. Right? So when you look at the universal graph where you substitute each vertex with a click of size omega, omega is about T log n, then it becomes universal for n-vertex subgraphs of this, which is exactly what the thing we cared about. And why don't we pay too much when we do this click substitution? Well, the universal graph Gn had a near linear number of edges. Then when we do the click substitution, each edge becomes a complete bipartite graph with omega squared edges. So we essentially pay an omega squared factor. I'm forgetting about the edges of the click. And this omega was T log n, so omega squared is T squared log squared n. So T squared is here, and the log squared n is hidden in this big O notation. Right, so if you can do C log n times Pn, the n-vertex subgraphs of this, then you can actually do n-vertex subgraphs of this as well. And so you can do the planar graphs in particular. So let me have a quick look at the time. Okay, so it's good. It's enough to look at universal graphs for n-vertex subgraphs of this. And now we have a clean problem. We have a really clean problem. This is a nice graph to think about. But unfortunately, this is where the proof becomes less clean. So from this point on, I will just try to give some of the intuitions without going much into the details. So again, what is the goal? We look at n-vertex subgraphs of C log n times the path on n vertices, and we want to find a universal graph with few edges. What will be the vertices of our universal graph? There will be triples, x, y, z. Z is not really interesting. So first, x, y, z are bit strings, code words, sequence of 0 ones. And z is a short string, log n bits. It's not really interesting, and I won't spend too much time on this. X and y are the important part. They each correspond to somehow a dimension. X will correspond to the horizontal dimension in the product, and y will correspond to the vertical dimension of the product. And together, x and y, when you sum up the lengths, they sum up to log n plus leader of log n bits. So that will be important. So if you manage this, then you can see that at least the number of vertices in your universal graph is at most this near linear upper bound. So I didn't tell you at all how we put the edges, but at least in terms of number of vertices, we are good. Okay, so what is the meaning of x and y? Well, x and y will encode a position in some binary search tree. Let's start with y. So y will encode the position in some vertical binary search tree. And by vertical, I mean that you're going to think about this vertical path, and you are looking at the rows, and each row will be put somewhere in this vertical binary search tree. and Y will encode the position in that binary search tree of the row. X will encode a position in a horizontal binary search tree. But now the difference is that it's not global. You have one horizontal binary search tree for each row in your product. So maybe it's helpful to look again at the product, right? So for each row, you will have a corresponding binary search tree. So this is row 1, row 2, row 3, etc. And you will have a BST for each row. There is only one vertical BST, but one horizontal BST for each row. And all these binary search tree will be almost perfectly balanced, right? So if you have k elements in one of these BSTs, then you would like the height to be about log k, log in base 2 of k. Okay, so now I'm not going to explain how we put the edges between these vertices of your universal graph. What I'm going to do is I'm going to try and give some idea of how do we embed a given graph into the universal graph. So we are given some specific graph G on n vertices, which is a subgraph of this graph C log n times Pn. And we want to embed G as a subgraph of our universal graph. And now I'm going to say a few words about how we do the embedding. And hopefully this will convey an idea of what kind of edges we need to anticipate in the universal graph. And hopefully you will get an idea that indeed there are not too many edges to anticipate. And indeed there is a way to only put a near linear number of edges. So this is the part where I will be a bit more vague. Oh, first, maybe I should recall what a binary search tree is. So that's a binary tree. It stores some values. In this case, it will be positive integers from 1 to n. And the key property is that when you look at some node that has value I in your BST, then on the left subtree, you have everything which is less than I. In the right subtree, you have everything which is bigger than I. So let's look a bit at this vertical BST, because that one is quite simple and quite natural. So we are going to look at the rows. So what are the rows? Well, they correspond to vertices of the path. So we are going to number the vertices of the path from 1 up to n, say from top to bottom. And we are looking at the rows, the row weights. How many vertices of a given row are used by the specific subgraph we are looking at? And now we are going to put these numbers, so the numbers from 1 to n, so the row numbers into the BST, which should be perfectly balanced. But we want to bias it according to the weights of the rows. So rows with high weight should be close to the top. There is a standard way of doing this. So of course, like if you have like uniform weights, say each row has weight 1, then your BST will look like this essentially. So the middle row will be on top, and then you split evenly, as you might expect. But more likely, when you look at a specific subgraph, you will have lots of rows that you're not using. Then maybe some rows will have heavy weights, like row 6 and row 10 in this figure, and then some rows have smaller weights. So then these heavy rows, they have to be close to the top in your embedding. But there is a standard way of doing this, a weight biased BST, and that's what we are using here for the vertical part. So this is completely standard. What will be a bit less standard is what we do for these horizontal BSTs. So, so what is the goal here? We are looking at some row I, and we look at some copy of C log n, this graph that we have in row I, but we are in the specific subgraph G that we are looking at from the product. We are only using a subset of the vertices of C log n in row I. So when you look at C log n, well, first I need to put some numbering on the vertices of that graph. And of course, I will use a numbering which is suggested by the underlying complete binary tree. So if you were using all the vertices from your copy of C log n in row I, then a corresponding BST, which is perfectly balanced, is simply copy the corresponding order. but more likely you will only use a few vertices from a given row, like 6, 5, and 7 in this example. And then you want your BST to be perfectly balanced, so you will map them maybe in this way. Okay, so for each row, we are storing whatever vertices of C log n we are using in that row in a corresponding BST just for that row. And we want that BST essentially to be perfectly balanced. Okay, now at this point, you could say, okay, fine, I can look at each row independently. And for each row, well, I can look at whatever vertices I use and I can create a perfectly balanced BST from scratch and containing those vertices. That's one option, but this is not a good option for building sparse universal graphs. And intuitively, why is it not a good idea? Well, imagine that you have some vertex like vertex 6, which appears in row I, but maybe it appears also in row I plus 1, row I plus 2, row I plus 3. So this vertex 6 is used in many consecutive rows. Well, if you build these BSTs completely independently from one another, then the position of 6 in row I has no connection to the position of 6 in row I plus 1, in the BST on row I plus 1. And so why is that bad? Well, it's bad because then in terms of the universal graph, then you have to anticipate all the ways 6 could move from one vertex in your BST to another vertex in the next BST. And then you would need to anticipate all these moves and put edges for all these possible moves. And that's way too many edges. So this is really at the intuitive level, but what we want to do is we want to make sure when we go from row I to row I plus 1, a given vertex, if it survives, it can move, but only to a few positions. And that's where we have the technical part of the proof, is that the engine of the proof is what we call bulk tree sequences, which are a dynamic data structure for maintaining almost perfectly balanced binary search trees. And they are built dynamically. So we start from row 1. In that case, we just look at what is used in row 1 and we put a perfectly balanced BST there. And then when we go from row 1 to row 2, well, some vertices appear, some vertices disappear. So these are insertions and deletions in your BST. There is essentially only one way to do insertions and deletions in BSTs. That's fine. But then after we did those, we rebalance using some homemade recipe of rebalancing. And we make so that we rebalance in such a way that at every time, the new BST has almost optimal height. So if you have R sub I vertices in the ith BST, then you would like to have height to be log of that number of vertices. And then we allow a little bit of slack, which is some little of log n. And so the rebalancing will allow that, so that the BSTs, they stay almost optimal in height, but the BST in row I plus 1 will be strongly correlated to the BST in row I, in the sense that when a vertex moves, a vertex that survives from row I to row I plus 1, if it survives, it can only move to a few positions, big little of log n. So big O of square root log n log n. So these are the two main properties that we ensure in the rebalancing move. So there is a lot to say, and that's outside of the scope of this talk, because this is a bit technical. The paper is on archive, but this is really what makes this scheme working, is that we can have these BSTs that when they go from one row to the next, they undergo only minimal changes. And then when you translate this back to putting edges in the universal graph, you only have to anticipate a few possible moves. And because you only have to anticipate a few possible moves, you only have to put few edges. That's the intuition. There are lots of things that I didn't explain, but I think that's probably good enough for in terms of intuition about what we are doing here. So yeah, I see that we're already almost out of time. So let me, if that's fine, maybe let me say a few more words and then conclude. So that's what allows us to get a near linear bound for planar graphs. And it works as for any class of graphs that has this type of product structure theorem. So this includes graphs that you can embed on a fixed surface. That it's not difficult. Once you have the result for planar graphs, it's not difficult to show that graphs with Euler genus G, they are subgraphs of h times p, where h has attributed roughly to G. So we get universal graphs with near linear number of edges in that case. Another case where we get such universal graphs is for those K-planar graphs I mentioned earlier. So Dujmović, Morin, Wood proved last year that if you have a K-planar graph, then these graphs are subgraphs of h times p, where h has attributed roughly k to the 5. So for fixed k, again, you can find a universal graph with a near linear number of edges for those. But this is about what we can say about extensions beyond planar graphs. So this product structure theorem, of course, is much less expressive, much less powerful than separators, but it allows better bounds for universal graphs. I was planning to talk about induced universal graphs. I'm not going to really talk about induced universal graphs at all, and I'm already out of time. So I'm only going to say 2 words. In that setting, you want to realize the graphs you care about as induced subgraphs. And the problem becomes to minimizing the number of vertices, not number of edges. And this is not trivial because you cannot take a complete graph. And for planar graphs, this is a much studied problem. And there has been improved bounds on the number of vertices up to last year, where Bonamy, Gavoille, and Pilipczuk proved an n to the 4/3 bound using the product structure with a really nice proof. And using a different but related constructions, we get a near linear bound on the number of vertices. It again uses the product structure, uses these bulk tree sequences, but there are differences between the 2 constructions, but let me not go into that. So let me conclude with open problems. So for universal graphs, I would really like to know what happens if you forbid a fixed minor. So if you forbid an arbitrary minor, we still don't know a better bound than n to the 3/2 on the number of edges for your universal graph, which is what you get from separators. And it's not true that if you forbid an arbitrary minor, you get a product structure theorem. There are cases where you don't get such theorems, so you cannot use that. For planar graphs, well, we have a near linear upper bound. In terms of lower bounds, we only have these n log n lower bounds from trees. So for all I know, this might be the real answer. So it would be nice to tighten this up. And there are the corresponding questions for induced universal graphs. There, if you forbid a fixed minor, we only get the best known bound is n to the essentially quadratic in terms of for the number of vertices. And for planar graphs, we have a near linear upper bound on the number of vertices. But for lower bounds, we only have a linear bound, linear lower bound, not even n log n. All right. So let me thank you for your attention. Thank you very much.
Okay, thank you very much for a delightful talk. So if anyone would like to ask questions, please do signal in the chat or raise your hand or something. And maybe to start off, I could ask a question or two. So actually, first I wanted to ask sort of algorithmically. So these things are not too big. So if you generate one of these graphs, is it easy to find any specific? I hand you a planar graph. Can you find it in the graph?
So you mean the embedding in the universal graph?
Yeah.
Yes. So yes, this can be done efficiently. So the proof comes with an efficient embedding procedure, and it's not difficult.
Okay, great. And then the second thing I wanted to ask you, could you go back to the open problems, please? Yep. Fantastic. So in this excluding a fixed minor h, so are the lower bounds all n to the 1 plus little o1? So
no, as far as I'm aware, we only know the n log n lower bound from trees. I'm not aware of any better lower bound.
What's the smallest h for which
okay,
it's open?
So that I can answer precisely. So we know exactly when we have a product structure theorem. So when you forbid a fixed graph h as a minor, if h is an apex graph, So there is a vertex you can remove so that you get a planar graph from H. So if H is apex in that sense, then if you forbid H, then there is a product structure theorem. If H is not apex, so if it's not true that you can find a vertex that you can remove from H that you get a planar graph, then the graphs you get by forbidding H as a minor, they simply don't satisfy a product structure theorem. So it's not that we don't know one, it's that there is no one. There is no product structure theorem, at least in the form that I stated. So for all non-apex graph H, I don't know any better bound than n to the 3/2. And for every apex graph H, we know a near linear upper bound.
So that means, let's say K5 is good, but K6 is open. Yeah.
Exactly. K6 is a very nice example, for instance.
Okay, very nice. I had one final question, which is a slightly vague question. But so these universal graph constructions, if you kind of think about what the universal graph looks like, they have great big cliques. I mean, they've got a sort of log or polylog clique embedded in them.
Right.
If I understood the construction. Yeah. So is that in some sense necessary? Do you have to have large cliques if you're going to have a small universal graph? So I mean, I imagine I'm sure you can show it's not, you can't be kind of close to planar, but must you be kind of very far in that sense? Okay,
so your question would be like, is it true that in every universal graph, say for n-vertex planar graphs with a near linear number of edges, is it true that you always have, say, a polylog n clique?
Yeah, or cliques of unbounded size even, just
cliques of unbounded size.
Just.
Yeah, I don't have a definitive answer. I don't see how to avoid them, but I don't have an answer to that. That's a really nice question.
Okay, thank you. If we don't have any other questions, let me stop recording.